A coil of 1200 turns, mean area 500 centimeters square, is held perpendicular to uniform magnetic field of induction 4 into 10 power minus 4 Tesla. The resistance of the coil is 20 ohm. When the coil is rotated through an angle 180 degrees in a magnetic field 0.1 second, the average electric current induced is. Now we'll calculate flux. Flux is equal to B dot A, that is equal to BA cos theta. BA cos theta. We have n turns, then you will get I and BA cos theta. So change in flux I will calculate. Phi 2 minus phi 1 is equal to NBA cos phi minus NBA cos 0. That is equal to cos pi is minus 1 minus 1, that is equal to minus 2 into NBA, that is equal to minus 2 NBA is the change in the flux. Here N is equal to 1200 turns and B is equal to 4 into 10 power minus 4 Tesla. Resistance is 20 ohm. The coil is rotated 180 degrees. Okay. Now the time t is equal to 0.1 second. Then we know E is equal to d phi by dt minus d phi by dt. So minus of minus 2 NBA is equal to 2 NBA, that is equal to, let's substitute the values. 2 into N value is 1200, B value is 4 into 10 power minus 4, and area is 500 centimeters square, so 10 power minus 4. Right. Now this value by 0.1, that is equal to, so this is two zeros, 10 power minus 4, 2 12 are 24 into 4 5 are 20 into 10 power minus 4, this when it comes up 10 power plus 1, so 10 power minus 3 is E. Now E is equal to IR, so I is equal to E by R. E is 24 into 20 into 10 power minus 3 by R. Resistance is 20 ohm. Resistance is 20 ohm. So this 20 and this 20 gets cancelled. 24 milliampere. A rectangular coil of length 0.2 meters, 0.1 meter, having 50 turns, suspended vertically in a uniform magnetic field strength 0.2 Weber per meter square, carries a current of 2 amperes. If the plane of the coil is inclined at an angle 30 degrees with the direction of the field, the torque required to keep the coil in the stable equilibrium will be. Now let's calculate what is the torque acting on it. The torque acting on it, the torque acting on it is equal to M cross B, which is equal to M B sin theta. M is I into A into B sin theta. If you have n turns, then NIAB sin theta. Now here n is number of turns. Number of turns are 50. So 50 into current is 2 ampere into area is 0.2 into 0.1, that is 2 into 10 power minus 2 into B is 0.2, so 2 into 10 power minus 1, and sin theta, sin 30 is 1 by 2. So this 2 and 2 gets cancelled. This is 100, this 100 and this 100 gets cancelled. That's 0.2 Newton meter torque. A coil is in the shape of an equilateral triangle of side 0.02 meters. Form its workpiece such that it is hanging in vertical plane between the pole pieces of permanent magnet, producing uniform field of 5 into 10 power minus 2 Tesla. The current of 0.1 ampere is passed to the coil. What is the couple acting? Again, this question is based on the torque. Torque is equal to M cross B, which is I into A is M into B. N number of turns are there, N into sine theta. Sine 90 here because it is placed perpendicular. So we get N I A B. Now let's calculate the area over here. Area is equal to, now is it in the shape of an equilateral triangle. So this is an equilateral triangle. Area is half into base into height. So this is base, this is height. So that is equal to half into base is 2 into 10 power minus 2 into height. Height is root 3 a by 2 for an equilateral triangle. So we get the side is 0.02. So I just substitute over there. So half into 2 into 10 power minus 2 into root 3 by 2 into A value is 2 into 10 power minus 2, which we get the value as root 3 into 10 power minus 4 meter square. 2 cancel here, 2 cancel here. So root 3 10 power minus 4 meter square. Now I'm going to substitute this area value in this. N number of turns is 1, so current value is 0.1 into area is root 3 into 10 power minus 4 is area. B value is 5 into 10 power minus 2. Just have to multiply this value. So we get 5 root 3 into 10 power minus 7 Newton meter. A square loop ABCD carrying a current I placed near and coplanar with the long straight conductor XY carrying a current I. The net force on the loop will be. Now the current I is moving in this direction. Here the current is moving in this direction in this loop, and here the current is moving in this direction. In AB it is in this direction, and CD it is in this direction. So now the AB and CD contribute to the net force because the force acting on BC and AD will be 0 because they are perpendicular. So now these two are in the same direction. So these are attractive force. These are in opposite direction. This XY and CD are in opposite direction. Opposite direction, if current is flowing in opposite direction, the force is repulsive. So first of all, the attractive force between XY and BA is F1. F1 is equal to mu naught by 2 pi into I by the distance between them is L by 2. So L by 2 into L. So this L and L gets cancelled. So I get mu naught by 2 pi I 2 I. Right. Now F2 is equal to F2 is the force on XY and CD. So that is equal to mu naught by 2 pi I by the distance from CD to Fi is 3L by 2. L plus 3L by 2 is 3L by 2. So that is 3L by 2 into L. So this L and L gets cancelled. We get mu naught by 2 pi. So this is 2I by 3. Now, as we discussed, this F1 and F2 are in opposite direction. F1 is attractive and F2 is repulsive. So the net F net is equal to F1 minus F2. That is equal to F1 is mu naught by 2 pi 2 I. If I take common, and that is 1 minus 1 by 3. That is equal to mu naught by 2 pi 2 I 1 minus 1 by 3. So it is 3 minus 1 by 3, 2 by 3, 2 by 3. So this 2 and this 2 if I cancel, then it is 2 mu naught I by 3 pi. This first option. Two long wires. Two long wires are hanging freely. They are joined first in parallel, then in series. Then they are connected with a battery. In both the cases, which type of force acts between the two wires? Now, parallel. When they were connected in parallel, then both of them will have same direction. Same direction means attractive. Same direction is attractive. Now, when you connect them in series, connecting them in series means, so the current will flow like this. Here current will flow in this direction, here the current will flow in opposite direction. So opposite direction means repulsive. So in series we get repulsive, whereas in parallel we get attractive. So attractive force when they were in parallel, and repulsive forces when they are in series. A closed loop PQRS carrying current is placed in uniform magnetic field. If the magnetic forces on the segment PS, SR and RQ or F1, F2 and F3 respectively, and or in the plane of paper in the direction, then the net force on the segment QP is. Now this is the figure. Now the F1 is acting in this direction, F3 acting in this direction, F2 acting in this direction. We have to calculate the force on PQ. That is, we have to calculate the force here, F4. Now we know that the sum of all the forces in a loop is equal to 0. So F1 plus F2 plus F3 plus F4 is equal to 0. That means okay, these are vectors, so we have to add them vectorially. So F4 is equal to the F1 plus F2, F1 plus F2, of course it acts in opposite direction to this, plus F3. Now if you look at this one, F1 minus F3, so the net of F1 and F3 is, let us say, F1 is greater, or F3 is greater, because in the options F3 is there, so I will write F3 is greater. So the net is along x-axis is F3 minus F1 along the x-axis, and along y-axis it is F2. So this is F2. The angle between them is 90 degrees. So the resultant force of these two is equal to root of F3 minus F1 whole square plus F2 square. F3 minus F1 whole square plus F2 square. When a proton is released from rest in a room, starts with an acceleration a naught towards west. It it is projected towards north with velocity v naught, it moves with the initial acceleration v a naught towards the west. The electric and magnetic fields in the room are. Now, so here, when it is released from rest, it is accelerating towards west. When it is projected towards north with speed v naught, it is accelerating towards west. Now, the magnetic field does not or cannot accelerate the body. Right? The change in kinetic energy due to the magnetic field will be equal to 0. So, this is definitely due to the electric field. As it is due to the electric field is towards the west. So, we know that electric field is towards west. Now, let us write the acceleration. A naught is equal to E by M. E by M. Then electric field is equal to M A naught by E. So this is the magnitude of the electric field. M A naught by E towards west, M A naught by E towards west. Okay, so it will be in option 1 and 2. Now, A naught is equal to E by M. E is equal to M A naught by E. Okay, is E. Right, we got E. Now we write the net F by total F net by mass is equal to 3 A naught when it is accelerating along 3 A naught. That case we will discuss now. Now both magnetic field and electric field were acting. So E EV, so E into E naught into E, this is the force exerted due to magnetic field, and E into E is the force exerted by the electric field by mass is equal to 3 A naught. Now here E V naught B plus E E is equal to 3 M A naught. Now here E E is equal to M A naught. So I will use this condition here. E V naught B is equal to 3 M A naught minus E E. But E is equal to M A naught. So 3 M A naught minus M A naught is equal to E V naught B. I will write it over here. So E V naught B is equal to 2 M A naught. So I want B value. B is equal to 2 M A naught by E V naught. And by using the left hand rule, we can find the direction is upward. A uniform electric field and a uniform magnetic field are produced pointed in the same direction. An electron is projected with its velocity pointing in the same direction. Then electron will turn left, right, or increase in magnitude or decrease in magnitude. We need to calibrate. Now the force due to the magnetic field, that is equal to QVB sine theta. Now as they were projected in the same direction, the magnitude of the magnetic field, it is equal to 0. Now force due to the electric field is equal to force due to the electric field. See here, the this is force due to the electric field. We write it as F is equal to QE. Now let's see the direction. So this is positive. From positive, electric field direction is this. In this direction, if you project a electron project an electron in this direction, then it will be pulled in this direction, so the velocity will get decreased. Okay, so the velocity will decrease in magnitude because it will be pulled in this direction. A rectangular loop carrying current I is situated in the long straight wire such that the wire is parallel to one of the sides of the loop and is in the plane of the loop. The steady current I is established in the wire as shown in the figure. The loop will. Now here this current is in the same direction, so this will be attracting in this direction. Here the current is in opposite direction, so this will be repulsion. Here this is the force is inversely proportional to the distance, so here this force will be greater. So it will be moving towards the attractive force is greater, so it will move towards the wire. A long hollow copper pipe carries a direct current. The magnetic field associated with the current will be. So now this is a hollow one. So if you consider an Amperian loop, then you will get outside only, because inside you will get 0. Integral of E dot ds is equal to mu naught into current enclosed. The current enclosed inside will be equal to 0 because it is hollow. So only outside we will have. So only outside the pipe. Two thin, long, parallel wires separated by a distance p, carry I amperes each. The magnitude of force per unit length exerted by one wire on the other is, let us take this distance as b. Then force per unit length is equal to mu naught by 2 pi I into I square by b, mu naught I square by 2 pi b. A proton moving with a constant velocity passes through the region of space without any change in its velocity. If E and B represents electric and magnetic fields respectively, this region of space cannot have electric field not equal to 0. If you have electric field, then it will be moving in that direction. A circular current carrying coil has a radius r. The distance from the center of the coil on the axis with the magnetic induction is 1 by 8 of its value at the center of the coil is. Now P naught by P is equal to 1 plus x square by r square whole power 3 by 2, where P naught is magnetic field due to the coil at the center and magnetic field due to the coil at the center, and the on the axis at a distance x field is P, at the center it is P naught. The relation between them is P naught by P a is equal to 1 plus x square by r square whole power 3 by 2. Given that this is P a is 1 by 8, 1 by 8. So B naught by 8. So 8 will go up. So 8 is equal to 1 plus x square by r square whole power 3 by 2. So this I can write it as 2 cube. 2 cube is equal to 1 plus x square by r square whole power 3 by 2. Then cube root on both sides, we get, applying cube root, 2 is equal to 1 plus x square by r square whole power 1 by 2. Then squaring on both sides, this will become 4, 1 plus x square by r square. Then x square by r square is equal to 4 minus 1 is 3. So x is equal to root 3 r. A magnetic needle is kept in a non-uniform magnetic field. It experiences force and torque. Force and torque. An electron is moving with a speed 10 power 8 meter per second perpendicular to the uniform magnetic field of intensity B. Suddenly, the intensity of magnetic field is reduced to B by 2, the radius of the path. The radius of the path. R is equal to mv by bq. Now, all of them were constant, so the relation we can, remaining all were constant, so the relation is constant, so the relation I can write R is inversely proportional to B. Now, when B reduces by B by 2, then R increases to 2R. Or else you can write R2 by R1 is equal to P1 by P2. You just substitute the values, R2 values will get it 2R. A current I amperes flow in loop having circular arc of radius R meters obtaining an angle theta. Shown in the figure, the magnetic field at the center O of the circle is mu naught by 4 pi I theta by R. In the figure, there are two semicircles of radius R1 and R2 in which the current I is flowing. The magnetic induction at the O will be. Now, if you curl your fingers in this direction, thumb points downward, thumb points. Curl your fingers in this direction, thumb points downward, so magnetic field is downward. Now here, if you curl your right hand fingers in this direction, your thumb will be pointing inward into the plane. Both the fields, the field produced by this and the field produced by this, are in the same direction, that is towards the into the plane. So the net B is equal to B1 plus B2. The magnetic field due to this one is equal to mu naught I by 4R for the semicircle, or R1 plus, now for this semicircle it is mu naught I by 4 R2, that is equal to mu naught by 4 mu naught I by 4 into 1 by R1 plus 1 by R2 is equal to mu naught I by 4 R1 plus R2 by R1 and R1 R2 R1 plus R2 There is a magnetic field acting in the plane perpendicular to the sheet of paper, downwards into the paper as shown in the figure. The particles in the vacuum move in the plane of the paper from left to right. The path indicated by the arrow could be traveled by. Now you use the uh, Fleming left hand rule. Fleming left hand rule. Your index finger should be pointing to the direction of the magnetic field. Your central finger should be pointing to the direction of velocity. Then your thumb denotes the direction of force. Now, if this is a positively charged particle, then the force would have been in this direction, but it is in opposite direction. That means it is not a positively charged particle, it is a negatively charged particle. So it is electron. A helium nucleus makes a full rotation in a circle of radius 0.8 meters in 2 seconds. The value of magnetic field B at the center of the circle will be. Now, I is equal to Q by T, that is equal to Q by time period is 2 pi by omega, so 2 pi omega here. So it is omega by 2 pi. Now, if I write the values for Q, Q is the charge of the charge. Now, charge of the helium nucleus is 2 into charge of the helium nucleus is 2 into 1.6 into 10 power minus 19 into right by by what is this omega by 2 pi frequency, that is is 1 by t is equal to 1 by air, so that gives here 2, so that 2 and this 2 will get cancelled. Get I is equal to 1.6 into 10 power minus 19 amperes. Now magnetic field at the center is equal to B is equal to mu naught I by 2R. Substitute the values. U naught is equal to uh, uh, U naught is already there here, so U naught into I is 1.6 into 10 power minus 19 by radius is 0.8. If radius is 0.8, so this is 2 into 0.8. 2 into 0.8, 1.66 cancel. Mu naught into 10 power minus 19. Mu naught into 10 power minus 19. An electron of mass 0.90 into 10 power minus 31 kg under the action of magnetic field moves in a circle of radius 2 centimeter at a speed 3 into 10 power 6 meter per second. If the proton of mass 1.8 into 10 power minus 27 kg were to move in a circle of same radius in a magnetic field, then its speed will be. Now we know that R is equal to mv by bq. R is equal to mv by bq. So we can write bqr is equal to mv. Right. So here the radius is same, q is same, v is same. So I will write mass of proton into velocity of proton is equal to mass of electron into velocity of the electron. Then here the speed of the proton we have to calculate. So velocity of the proton is equal to mass of the electron into velocity of the electron by mass of the proton. Now these values were given, just we will put the values of mass of the electron, which is mass of the electron, yeah, 0.90 into 10 power minus 31 into velocity of the electron is 3 into 10 power 3 into 10 power 6 by mass of the proton is 18, so 1.8 into 10 power minus 27 kg. So if you do the math, then 1.5 into 10 power minus 10 power 3, 10 power 3 meter per second. Two long straight wires are set parallel to each other. Each carries a current in the same direction, and the separation between them is 2R. The intensity of magnetic field midway between them is. Now this is one wire and this is another wire. The midway. Now midway between them is. Now if we calculate the magnetic field, use the ampere right hand thumb rule. If thumb denotes the direction of the current, the direction in which your fingers curl denotes the direction of magnetic field. So imagine a current carrying conductor. If we put a thumb here and curl our fingers like this, and imagine a hole here, then your fingers will be coming out from this hole. So it is upward due to this wire, and due to this wire, imagine holding a current carrying conductor. Your thumb is here. Your fingers, if you try to here it will be upwards. Here, when we put our fingers, the fingers will be coming down from this and they will be going into it. Okay, so this one will be going into it and this one it is going outside. So these two are equal and opposite. The magnetic fields are equal and opposite because same current is flowing and the distance is same. So they will cancel out each other and the field will become 0. Right? Here we have to place the fingers here, the thumb here, curl your fingers, then your fingers might be going into the plane like this, downward. So this is downward, and for this one it is upward. Magnetic field is upward. These two are equal and opposite, so they cancel out each other. So the net field will be equal to net magnetic field will be equal to 0. An electron is projected along the axis of a circular conductor carrying some current. The electron will experience a force. So if you imagine that the current is flowing in this direction, then if you curl your fingers, then it will be outward. Now it will be outward. If it is outward, and the electron is coming in this direction, then theta will be 180. So the force will be equal to 0. Now, if the current is in clockwise direction, imagine current is in clockwise direction, then field will be downward. So if it is projected, if the electron is also in the same direction, then that sign 0 is 0. So F is equal to, force is equal to 0. So it is PQV sin theta. Force is equal to PQV sin theta. Now here the theta will be either 0 or 180, then force will be equal to 0. So it will not experience any force. A proton and an alpha particle are accelerated through the same potential difference, then enters into a region of uniform magnetic field P at right angles to it. The radius of the proton circular path is 10 centimeters. Proton circular path is 10 centimeters, then radius of the alpha particle's path is. Now we know that R is equal to mv by dq, that is equal to, now this we can write it as P by dq. Now P is equal to root of 2m kinetic energy by dq, that is equal to root of 2m qb energy. It is potential, V is potential, Q is charge by dq. Right? Now they have same potential, so they have same potential, right? So root 2 is constant, so root m by dq. R is directly proportional to root m by dq. And the magnetic field is also same, so root m by q. So now for the radius of the proton, okay? Radius of the proton is root of m by q. Root is only for mass. Now radius of the alpha particle is root of, now it has got 2 protons, so it's 2m by charge is 2q, 2q, right? So it's alpha particle 4m by 2q. That is equal to right 2 by 2q. So 2 get cancelled. So again you will get root m by q, which is radius of proton. So radius of P will be equal to radius of alpha. So figure shows two wires between 2 points A and B. One is arbitrary shape is a and the second one is a straight wire, both carrying the same current. The wires lie in the field of magnetic induction D. Which one of the following is true? Now the force experienced by a current carrying conductor in magnetic field F is equal to PI L. Right? Exactly, it is L effective. Now for the first one, the initial point is A, final point is B. Final point is B. Now for this, so it will be equal to the force on 1 will be equal to force on 2 because both the initial points and final points for both of them are same. So the length for this one and 2, we have to consider it as same. So number 1 experiences same force